We finished in the previous class introducing the Routh procedure, basically which is an attempt, actually successful attempt, right, to combine advantages of the Lagrangian formalism and Hamiltonian formalism, right? And the basic idea is to treat cyclic or ignorable coordinates, it's better to use Hamilton's equation. So that's what Routh procedure does. And since Lagrange equation treats better non-cyclic coordinates, so that part, Routh procedure took that part from the Lagrangian formalism. Sort of as a result, we ended up with some kind of hybrid, right? Some kind of, I don't know, Frankenstein's creature, right? Where different parts of different pieces were combined. Right? Okay, so now let's look at the example, and then we'll move to new material. Right? Example. As I told you, we're going to beat this problem using different classical mechanical tools. Again, central force problem. Right? So let's apply our Routh procedure for this problem. All right. So we can write immediately Lagrangian. Right. We've done it so many times. All right. So L equals m over 2 r dot squared plus r squared theta dot squared and minus minus plus k over r to the power of n. So, and of course now let's see. All right. Theta is missing, so theta is cyclic, right? All right. Theta is cyclic, right? R is non-cyclic. So it means that we can use Routh procedure, right? And of course, in the Routh procedure, we will have to, since theta is cyclic, we will have to remove theta dots. Theta dots must be removed, right? But we're going to keep r and r dot because r is non-cyclic and it's better to use Lagrangian formalism, right? So, so in order to get rid of theta dot, of course, we need to prepare that ingredient, right? Which we can get from definition of generalized momentum, right? Basically, prepare a replacement for theta dot. Right, so you remember we have p theta equals to partial derivative of the Lagrangian with respect to theta dot. So that's the definition of generalized momentum. And of course, in our case, it will be what? Mr squared theta dot. Mr squared theta dot. And of course, from here, we will get the replacement, which we will need in a few minutes. So it will be p theta over mr squared. So our Routhian will have dependence on p theta. Theta is cyclic missing, and then r and r dot. Okay, so now let's write down the Routhian, which is of course that expression is based on Legendre transformation. We're going to use Legendre transformation many times in this semester. Right? So the Routhian, which is r, again function of, okay, theta is cyclic, right? Then instead of theta dot, we will have, okay, maybe I will use p theta, and then the second set of coordinates r dot, and possible time dependence, but in this case there is no time dependence also. T is also cyclic, right? Okay, and you remember how we constructed, again, using Legendre transformation, but only now we're going to replace only theta dots, right? So you remember in Legendre transformation, first you need to multiply, create a term which is the product of old variable which you want to remove times the new variable which you want to introduce into a new function. So old variable, of course, it's a theta dot, new variable p theta, and minus the Lagrangian. Right. So now, of course, we don't have r dot pr because we don't want to replace r dot in the Routhian procedure. So that's the Okay, let me check. Yeah, of course, that's the correct. And so now let's write down explicitly. So it will be p theta theta dot. In this way it looks better. And then minus, right, m r dot squared over 2 minus m r squared theta dot squared over 2 in minus potential energy k r to the power of n. Okay, so now we just need to, again, it's sort of not a complete Ruthian. We can call it pseudo-Ruthian because we still have theta dots, and now we have to use ingredient which we prepared in advance, right? So this ingredient, right? So we can take that and plug it here, and of course there. Right. Okay, so now, of course, we will get p theta squared over mr squared, right? This term. Then, okay, nothing happens with that one. And over here, first we have to square it, so we'll get p squared, m squared r to the power of 4, and here we have mr to the power of 2, so downstairs we'll have exactly the same denominator, but with a factor of 2 also. So it will be, and with minus p theta squared over 2 mr squared, right? And the potential energy, we're almost done, k r to the power of n, right? So this and this goes. Okay, they just partially cancel each other. So p theta squared over 2 mr squared minus kinetic energy and minus potential energy. Okay, the Ruthian, right, which is the function of p theta, r, and r dot, and time, of course, missing. Probably I should also kind of, right, remove this because there is no explicit time dependence. Right? Okay, this is, of course, very important. So worth of framing. Right? And so now we need to write down how many equations? 3 equations. One first order, second order differential equation, which is Lagrange equation, and then 2 Hamilton's equations, which are first order differential equations. So overall 3. So let's start with Lagrange equation. So it will be d over dt partial derivative of the Ruthian with respect to r dot minus partial derivative of r with respect to r and equals to 0. So second order differential equation. So let's write explicitly. Will be r dot only 1, so we'll have mr dot and then another dot. It will be double dot and minus in front. So it will be minus mr double dot, right? Then this minus, okay, let me put minus in front because chances I can lose it somewhere high. Okay, so respect to r here, it will be another minus, factor of 2 will go, p theta squared over mr to the power of 3. So differentiation of this, differentiating this, and then here. So we'll get minus and minus give us plus. It will be plus nk and r to the power of n plus 1, right? And it must be equal to 0. So that's the differential equation, second order. Let me check if I got what I was planning to get. You know what I'm getting? No, it's good, it's good. No, it's good. Okay, you can multiply by minus 1. Okay, I don't want to rewrite it one more time. It's basically the final form, right? Typical equation for a central force problem, right? Okay, so now the second, which one I will probably, okay, let's start with p theta dot. P theta dot equals to minus partial derivative of the Ruthian with respect to theta. But of course, theta is cyclic. We knew it from the very beginning. We saw it, right? So this is 0, of course, equals 0. And as a result, the corresponding generalized momentum is constant, right? Okay, so that's what, again, that's basically the advantage of using Hamilton's equation, that immediately you're getting the answer P, right? And now the last equation, which is theta dot, all right, equals to partial derivative of the Ruthian with respect to P theta, right? Okay. P theta only here, so 2 gets cancelled, so we'll get P theta over mr squared. P sub theta over mr squared, right? Yeah, of course. Okay, so of course from here we can solve for P theta. It will be equal mr squared theta dot. So it's a, yeah, angular momentum like what we had before in the central force problems. Right? Of course, you can combine this, right? So you can also write that this is equal to constant, the last two equations, P theta equals constant. Okay, so exactly the same equations at the end using the Ruthian procedure, right? Again, as I told you, the Ruthian approach, it doesn't give you any deeper understanding of how mechanical system behaves, live its life or evolve. No. It just make life maybe a little bit easier in terms of mathematics, slightly, right? But in terms of physics, not much of advantages. All right. But I like it because discussing Ruthian procedure, you can discuss advantages of the Lagrangian formalism and Hamiltonian formalism, right? Enough of this. Now we need to move to a different chapter. We're still going to be within work within Hamiltonian formalism, but now it's the next chapter, chapter 9. And so what's the major idea of the next many classes? Several classes, right? Okay, so we can say we are experts in the Hamiltonian formalism, right? So we know how we can write down the Hamiltonian. Then, of course, we can write down Hamilton's equations, so we can describe behavior of pretty much any mechanical system, right? So no restrictions. So now we can say we are experts. So what's the next normal, natural response of any human being once you start feeling comfortable somewhere in some field, in some area? You start searching for simplifications. You start behaving sneaky, right? So how can I make my life easier, right? So it's sort of like at the beginning of the semester. Students first at the beginning of the semester, they're scared, afraid, they don't know new instructors. But once they start feeling comfortable, right? So they can say, this is a simple course. I will just sleep over that class, right? So this guy I should attend because he's a tough SOB, right? So this I can come occasionally just for test, right? So you start behaving sneaky, you start searching for shortcuts to simplify your life. It's absolutely normal. So now we are at the same stage in the Hamiltonian formalism. How can we simplify our life? At least somehow, right? And of course, so what can be done? We can we can use different coordinates, for example. Let's say you have some problem. You can set it up in the Cartesian coordinates, but it can be ridiculously complicated. But you don't want to struggle with those Cartesian coordinates. Maybe you can go to polar, or maybe spherical, or maybe elliptical, or maybe hell knows which coordinates, right? You can go to somewhere you cannot even recognize where you went, right? Or where you go, right? So that's what we want to get. We want to go to a different world to make our life easier, right? And actually, we can start sort of thinking big, right? So what's the ultimate place, the best place possible where you can go? It's the place where if you come there, the solution will be ready for you, basically like a gift wrapped. You need to just go there, grab that solution, and go back. As a result, instead of solving the problem in your original coordinates, all your efforts will be just in traveling to the new place, grab the gift, grab the solution, and go back. So instead of solving, you will just spend all your efforts traveling. Actually, we like traveling, right? It's more fun, right? Sometimes, right? Right. But of course, sometimes people like I go to one of the to have a haircut done. One lady, she's from Vietnam. What, 25 or 30 years ago, she escaped from Vietnam on a small boat in a rough water, right? So in that case, traveling is, she thought that they will all die, right? So it's not fun traveling, right? But anyway, so that's the idea, right? And very often, I said we don't want to go to some coordinates where we are not going to get a full range of simplifications. We want to get the ultimate place, right? So where the solution will be basically ready for us. And very often I compare with that the situation with the migration crisis, which was in Europe several years ago, right? You remember people going somehow through over the Mediterranean Sea, and then of course those people didn't want to go, for example, to Greece, right, or Poland or Ukraine, because there they will be able to get some advantages, but not the full range of advantages, right? So of course they all wanted to go to Austria or Germany because you can go there and you can get almost everything for free, welfare, right? You just go there and money will be given for you, and you can live your life happily, right? So we also want to find the place where the life will be great. So I usually sort of let's think big, right, and describe the world where we want to go in order to simplify the solution. What about if we go to the place, to that set of coordinates where Hamiltonian is constant and all coordinates are cyclic? It's almost the best place that you can think of. But actually, you know what, frankly speaking, we will go even deeper in maybe 5-6 classes, right? We will even try to achieve even better place, right? But for now, let me outline this our goal, first goal. So we want to get to that point, to that place where Hamiltonian is constant, and all coordinates are cyclic. And then let's write down what will be a solution, because as I said, in that case, solution will be basically ready for us. We just need to go there, grab it, and then go back. Because at the end of the day, you still live in your Cartesian coordinates. You want to go back and see the solution over there, right? Okay, so now let me write down the name of the chapter. It's basically Canonical Transformations. Right. It's a chapter 9, Canonical Transformations. And pretty much the whole chapter will be about going somewhere in an attempt to make your life easier, right? Again, in terms of solving the problems. Canonical Transformations. Right. Okay, and so what should I write? Probably, how can we simplify our life? Okay, let me title this. Go to use different coordinates. Go to different coordinates. All right, and so the best place. Okay, so let me outline the best place. All right, so it's sort of like that king's speech, I have a dream, basically, right? So let's dream big, right? And let's find the best place possible, right? So I have a dream. Oops. Strange symbols. All right. So best place. Best place. You know what? Let me remove this bracket. Best place. All right. So where if what h Hamiltonian is constant. Constant of motion, right? And then, okay, so it's a first and the second. What if best place if all coordinates are cyclic? Right. So let's see what we're going to get in terms of if we apply Hamilton's equation. Right. Okay. So as a result, let's look at the Hamilton's equations, and let me start with with the second one. Yeah. Right. So pi dot equals to minus partial derivative of the Hamiltonian with respect to qi. Q's are cyclic. All Q's are cyclic, so of course this is 0. Oops. This is 0. And as a result, we can write that pi's, all our generalized momenta are constant immediately, right? So basically, if you go to the place like this, you can tell immediately all generalized momenta, okay, angular momenta or linear momenta, they're all going to be constant. Let's call them alpha I, constant. So great, right? Then what about the? Then of course, what will be with Hamiltonian? So Hamiltonian, which is a function which we wrote it. Okay, let me write this way. So h equals to, so Hamiltonian will be a function of what? Q's are cyclic, so they're missing. So we're going to have h as a function of alpha 1 and all the way to alpha n, right? So Hamiltonian will depend only on those set of constants, right? Okay, so now what about the second equation? Hamilton's equation qi dot equals to partial derivative of h with respect to pi. Basically, we differentiate Hamiltonian, which is full of these constants, with respect to one of those constants. What are you going to get? Another constant, right? You will get another constant. Okay, of course it will be some complicated construction. So but anyway, it will be a constant. Okay, let's label that constant as omega I. So we have trivial first order differential equation where derivative equals to constant. We can easily write down the solution. Basically, we can say we know the answer. So qi will be equal to omega it plus a new set of constants betas, because we integrate, right? So we have this, right, and we have that. Okay, at this point, we need to clarify one small thing, right? How many constants of integrations are we supposed to have? We have q, okay, n generalized coordinates and n generalized momenta. So we're supposed to have 2n constants of integrations. How many constants do we have now, it looks like? We have n alphas, we have n betas, and we have now n omegas. How come? Are we getting 3n constants of integrations? Or what's the story? And the thing is, what is omega? Yeah, these are constants. But how did we get these omegas? So we differentiated h, which is full of those alphas with respect to one of those alphas. So basically you will get a constant. Yeah, it will be a constant, but full of alphas. So it's not a constant of integration, not a new constant of integration. It's just a constant which consists of some of those alphas. So yeah, at the end of the day, we still have two n constants of integrations as we should have, right? So omega, it's not a constant of integration. It's just a complicated construction of constants of integration, right? So that's the ultimate dream, right? So that's where we want to be eventually. But as I said, will make one or half a step deeper when we get to the Hamilton-Jacobi equation, but that will be after quite some time, right? So that's our ultimate goal, and of course, we will try to get here step by step, right? So let me write, it's our ultimate goal. It's our ultimate goal. So let's go there step by step. Right. And first, we need to define which coordinates are called canonical, which transformations called canonical, and then a few other things, sort of everything which is essential in our eventual trip to our ultimate goal, right? First, let's introduce, or define, not introduce, define which coordinates are called which coordinates are called canonical. All right. Okay, I will put a new bullet. All right. And canonical coordinates, very simple. Canonical coordinates are those coordinates where Hamilton's equations are correct. And it makes sense because how do we call Hamilton's equations? They are canonical. Canonical, it means the simplest possible and symmetrical. In this case, they're almost symmetrical except for the minus. So since equations are called canonical, so the coordinates are also called canonical. So let me write down the sort of definition because it's very important, right? in all this formalism, in all these procedures. So coordinates Qi, Pi are said to be canonical. Let me write definition. Canonical. Okay, so from now on, we're going to use this word almost every class many times. Canonical this, canonical that, right? Canonical, if, okay, I will just write exact definition for my notes. If there exists Hamiltonian H, which is a function of Q, P, and T, right? Q, P, and T. So such that Hamilton's equations are correct. Such that, all right, I can write, so Qi dot equals to, wait, partial derivative of H with respect to P, and the second equation for P dot. Pi dot equals to minus partial derivative of H with respect to Qi. So canonical equations are correct. Right. So that's definition of canonical coordinates. So let me frame it. Then, now, next. You remember in the Lagrangian formalism, I told you, right? We did not prove it because the proof is kind of tedious, right? I usually skip it. We discussed that Lagrange equation has exactly the same form. It doesn't matter where you go. If you go from Cartesian to polar, the form of the Lagrange equation is exactly the same. If you go from Cartesian to somewhere else, to some elliptical coordinates, the form of the Lagrange equation will be exactly the same. It doesn't matter where you go. But in the Hamiltonian formalism, we have to be careful. All right? If you go to some, if you change coordinates, the form of the Hamilton's equation is not guaranteed. So we have to be careful. So basically, we need to develop some procedure, right? Some equations. If you follow those equations, if you follow that procedure, it will lead you from a set of canonical coordinates to a new set of, again, canonical coordinates. So here we have to be careful. We cannot just grab any transformation, go somewhere expecting that Hamilton's equations will be still the same. No, here it's a game is slightly more complicated, right? Okay, so let me write down, and yeah, we'll write down the what I just said. So basically, canonical transformations, the title. Basically, canonical transformation leads us from a set of canonical coordinates to a new set of canonical coordinates, right? Okay, but first let me write the fact that we have to be careful with these Hamilton's equations and with the transformations. So which way I wrote? So the equations of motions, equations of motion do not retain their canonical form under all transformations. So we have to be careful. Let me state that because it's a very important. All right. Okay, I will probably put a new bullet, right, and write down the equations of motions. The equations of motion. Basically, Hamilton's equations. Hamilton's equations. Do not retain their form. Right. Okay, I feel like I need to change marker very soon. What? Under their canonical form. Okay, very important word. As I said, now we're going to use that everywhere. Canonical. Canonical form under all transformations. Under all transformations. So we have to be careful. Oh, it's a new marker. At the very beginning, it's difficult to use it. So we have to be careful. But I think it's still visible, right? Yeah. I don't know what's wrong with these new markers. It takes a bit, like 5-10 minutes before they start writing nicely and smoothly. Right. So again, we want to go from original set of canonical coordinates to a different world where which is also canonical. Coordinates canonical. So it basically means we don't want to go to some creepy place. Again, I usually compare with immigration. For example, like if you live somewhere, I don't know, in Austria, right? You don't want to go to some strange place. Let's take an extreme, I don't know, to North Korea, right? For example, right? So where the rules are completely different, right? Basically, equations of motions are completely different, right? And of course, adjusting it will be, yeah. Who wants that, right? Of course, you want to go from a nice place to another nice place. For example, you can go from Austria to Germany, right? So basically, you'll barely see any differences, right, in terms of lifestyle and so on. Or from Austria to England, or from Austria to New Zealand or United States, right? So basically, that's sort of we can compare with this situation, right? So we want to go from a nice place where we have nice Hamilton's equations to a different place which is also as nice, and again where Hamilton's equations are correct. Okay, so, and again, since not all transformations can lead us to a nice place, so we have to be careful, and we need to develop a set of rules, I don't know, criteria, right, some equations. If you follow those rules, you will get in a nice, you will end up with a nice place, right? Okay, so now let me write a few words about canonical transformations, and then we will start developing those rules. Right, and we will spend like a couple of classes playing with those rules. Right, okay, I can erase this. Okay, so we want to find a transformation, for example, okay, the old set of coordinates, we're going to denote all the time q small, p small. New set of coordinates, q capital, p capital, right? So from q small, okay, sub I, p sub I, to a new world, and this will be q capital, p capital. Okay, the difference between small p and big P, capital P, okay, at least the way I try to write them down. Here I don't have a bar underneath of P, here I have a bar, so that basically means P capital, right? All right, and of course, some transformation equations eventually we will have, of course. So transformation equations, Qi, which is a function of Q small, P small, possible time dependence, and of course, P capital transformation equations. And these coordinates are canonical, and these coordinates also we want to have canonical. It looks like I'm advertising Canon company. I should add a few extra letters, right? Canon. Right, so we want to find transformation. Okay, let me write transformation. All right, so that canonical form of Hamilton's equations, canonical form of Hamilton's equations is preserved. Right. Basically, it means that if you here have this, okay, only now marker started writing nicely. Right? It takes like 5 minutes. Right. So partial derivative of h with respect to pi and dot. Pi dot equals to minus partial derivative of h with respect to qi, right? Hamilton's equations. And here, of course, they preserve the form, form, and we will have now q capital dot equals to partial derivative of, of the Hamiltonian, new Hamiltonian with respect to the new generalized momentum. And, okay, so here it's called Hamiltonian. Here, they usually use letter K to denote new Hamiltonian. And probably the person who came up with this new name has a good sense of humor. It's called Camiltonian. If this is Hamiltonian, then this is Camiltonian, right? I remember when I first read it and I saw it, kind of, yeah, I laughed for some time. Right? So Camiltonian, but of course it's just simple, just okay, regular Hamiltonian. And all right, pi dot, of course, equals to minus partial derivative of k with respect to qi. So k, it's a Camiltonian. Basically new Hamiltonian. Again, if you use just, again, continue using just the word Hamiltonian, that's what I usually do all the time, right? But Hamiltonian is kind of funny, right? I like this. Okay, so that's, yeah, and of course, so this is called canonical transformation. So this transformation is called canonical. Okay, so this transformation is called canonical. Canonical. Right. Okay, so, okay, probably I should frame it with red. So we just go from one set of canonical coordinates to a different set of canonical coordinates, and the form of the Hamilton's equations gets preserved. But of course, as I said, not every transformation can lead you to this world. So we have to be careful. So now we need to derive a procedure, some set of equations. If you satisfy them, you will get to a nice place. All right. Okay, so now after this, so basically it was all still an introduction to this chapter. And now finally let's get actually the conditions. Okay, let me put a new bullet and down. Let's derive conditions which guarantee canonical transformations. Right. So let's derive conditions which guarantee canonical transformations. A canonical transformation. A canonical transformation. Okay, so now we're going to spend maybe 1.5 class going through this, right? You will see why. So, first of all, before we start deriving, let's recall section, I think it was 8.5, okay, chapter 8, where we derived these Hamilton's equations. Do you remember how we derived them from the first principle, from the Hamilton's principle? So we just grabbed Hamilton's principle, okay, the action, right, action integral, right? And we varied it. And the variation of that action must be equal to 0. From there, we got these Hamilton's equations. So we needed, let me write that down, right? So section, so recall section 8.5, right, where we derived Hamilton's equations. We derived Hamilton's equations. In which way? So we varied action, and variation of action must be equal to 0. From that, basically what I just wrote is Hamilton's principle, foundation of Hamiltonian formalism, right? As simple as that. Just now I realized, damn, it looks so simple, so trivial. And that's the whole foundation, right? Okay, and so if you write it explicitly, of course, it's a variation of what integral from initial moment of time to the final moment of time. And of course, here it should be Lagrangian dt, but of course you remember we wrote it in terms of p and q dot and the Hamiltonian. So it was something like this, p I q I dot minus h, right? And dt and close bracket, and it must be equal to 0. So instead of this is basically Lagrangian, right? Okay, and from here, varying it, we ended up with Hamilton's equations. And of course, from here, we ended up with qi dot equals to partial derivative of h with respect to pi, and pi dot equals to minus partial derivative of h with respect to qi, Hamilton's equation. So that's what we need to recall. And now, so let's use it. So again, we want to go from, right, let's say, let me draw something like this, from p small, q small, p small. The problem is set in these coordinates, right? So the true path, right? And then some wrong paths, right? So this is t1, t2, and we want to go to a different world using transformation equations, right? Sort of outlining them the whole situation. So again, transformation equations. And in the new world, of course, it will be, we can plot P versus Q, and it's still the same problem. So initial moment of time will be the same, right? Final moment of time will be the same, right? So there will be wrong paths. There will be true path. So we're moving from here to there. And of course, we want to have these are canonical, and we want to get those also canonical. It means that we want to have these equations over here and the same equations over here. It means that this variation in these coordinates must be equal to 0. And the same variation in terms of these coordinates must be also equals to 0 over here. So let me write down underneath this for these coordinates and the same for those coordinates. Okay, yeah, I can erase this. These new markers make usually a mess out of the whiteboard. Okay, so as a result, this must be true for the old coordinates, so variation of integral from t1 to t2 pi qi dot minus Hamiltonian, which is a function of q p t small, then dt equals to 0. And for these guys, for capital, I can write exactly the same, but now in terms of q capitals. T1, T2, P capital, Q capital dot minus Hamiltonian. Okay, not Hamiltonian, Camiltonian, K. Minus K, which is the function of Q, P capital, T, then conservation of brackets, another bracket, dt, and another bracket, and it must be equal to 0. So this must be true for these coordinates. My intentions was to write them just below this picture, and that below this picture. Actually, I could have fit. Why I didn't do it? Good question. Okay, so now this equals to 0, this equals to 0. So we can say this variation must be equal to that variation, right? And of course, if you look at this kind of not very deep, probably you can make a statement that this integrand only, right, must be equal to that integrand. But it's not the whole story. The rabbit hole is much deeper here. Okay, not much, but deeper, right? So it means that it's not just integrands must be equal. We can take any arbitrary, well-behaved, good-looking function. Well-behaved, I mean continuous. You can and you can also differentiate it as many times as you want. Then, if you take the total time derivative of that well-behaved function and add that to this integrand, it will be still equal to 0, and still this will be equal to that. So we can introduce an additional function f, which we are going to call a generating function. Okay, let me write that down. All right. Okay, so let me write this. These integrands can differ by the total differential form. Okay, so let me write this. These integrands not integrals, integrands, functions under the sign of integral, right? Can differ, but still it will be equal to 0, and this will be equal to 0. So we can still get Hamilton's equations in both cases, in both set of coordinates, even if you add something additional. Can differ by df over dt, right? Of some, and this function f can be a function of, which we wrote, function of q p t and q capital p capital t, and this function is called a generating function. You will see in a second, okay, not in a second, in a few minutes, why it is called generating function. Because it will eventually generate transformation, canonical transformation equations for us. Generating function called generating function. And again, f, it's an arbitrary but well-behaved. Well-behaved, again, it means it is continuous, and you can differentiate it as many times as you want or need. Right. Okay, so as a result, if we can add total time derivative to that, okay, so as a result, this integrand must be equal to that integrand plus this total time derivative. So let's write that down. So I can write pi ui dot minus Hamiltonian equals to p capital q capital dot minus Hamiltonian and plus total time derivative of this function, generating function f. Okay, but I still need to show. I claimed that we can add this function, total time derivative of that function, but let's show. Let's look at the variation of the integral of out of this total time derivative. Is it true? Right. Is it true? Okay, so let's look variation out of integral. So df over dt from t1 to t2. Yep. Of course, dt goes. And of course, we will end up variation out of. You just need to evaluate function f at the upper and lower limit at initial moment, at the final moment of time and initial moment of time, right? And function f is a function, in general, can be function of all these variables. So I can write that f at, which we wrote to simplify it, f of q at t2, right? Then q small, q capital at t2. Then what? Probably I'll just grab my notes. Then p at final moment of time. Okay, it's a p, no, p small, then p capital at t2, and then minus basically the same function but at t1. Right. I just don't want to rewrite it one more time. Right, so evaluated function f at upper limit and function f at the lower limit. And of course, now we still need to vary it. Okay, try to vary it. So you will get partial derivative of f with respect to q. Okay, actually, there are multiple of q's, right? So maybe I can write, okay, let's assume for the simplicity one. All right, and delta q at t2. What's the value of this term? 0. Right? Because variation at the end point, okay, these endpoints, right? 0. Because it doesn't matter which path your system, okay, you assume the system takes, right? All of those paths, right, must go through the endpoints. Okay, in this case, it's this endpoint, right? Of course, over here, we have beginnings, right? So variations of all these Q's and P's must be equal to 0 at T1 and T2. Right, so 0, right? And the same, I can write, of course, tons of these terms, but again, all of them will be equal to 0. So there's no point of repeating them all. Maybe I can write additional, right? So plus df over d, what's next? Q capital, variation of the Q capital, but again at T2. And again, variation of Q capital in new coordinates, again, 0. Right. Right. Okay, so as a result, yes, true. All this and plus all the way, and it must be equal to 0. So yes, variation of this df over dt gives us 0, so we can add the total time derivative to that integrand. Okay, so this is correct. This is correct. So now, next, let's look at this generating function. Let's spend a few minutes discussing this generating function. So right now I wrote that it can depend on, oh my god, how many variables, right? N. So, okay, let me write that down. Rewrite. So, okay, let me put a new bullet. And function f, which is the function of, okay, which we wrote with subscripts qi, pi, q capital, p capital, and t. Okay, so overall we have what? 4 n variables n plus time, right? N plus 1, right, time. So we have 4 n plus 1 variables on which function f can depend. But are they independent? Obviously, then they shouldn't be. They cannot be independent, because we're making transition from this q small, p small to q capital, p capital, and of course, somewhere we know that there will be, or there are transformation equations which connect q small, p small with q capital, p capital. And how many of these transformation equations? To n of those and n of those. So of course, these transformation equations are going to reduce number of linearly independent coordinates, right? So as a result, 2n connections. As a result, we're going to have 2n plus 1 linearly independent variables on which function f, generating function, can depend, right? So then plus 2n transformation equations, right? Okay, maybe let me rewrite them quickly. plus 2n transformation equations. As a result, it must depend only on 2n plus 1 independent coordinates. So f must depend on 2n plus 1 variables. Okay, so now the question. Yeah, we reduce number of linearly independent variables. Which variables should we take? Basically, function f works, it's a generating function. Basically, it works as a bridge between the old world and the new world. All right? Basically, it's sort of like a bridge here. So, of course, it makes sense, right, to take 50% of variables from the old set to our generating function and 50% of variables from the new set, right? I think it's logical, right? Mm-hmm. Right, so since f works as a bridge, so let's take 50% from QP, Q small, P small, and 50% from Q capital, P capital, and 50% of Q capitals, P capitals. And of course, time dependent is still possible, but that plus 1 all the time will be there. Time dependence is still, in general, possible. Okay, so as a result, we're getting 4 possible combinations on which 4 possible combinations. As a result, we can introduce 4 types of generating functions. So the first one, as a result, so we can write f1 will be a function of, all right, probably I will start, no, let me write first without subscript. Q small, Q capital, and time. First, we take 50% of old, 50% of new, plus 1, 2n plus 1. So it's a first generating function of the first type. Now the second type, f2. Right. So it will be still Q small, but now we will take P capital and time. So now you see we're looking at all possible configurations. Right. Then, okay, you got the logic. Now f3. Right. So it will be a function of, now we need to change to P small, Q capital and time. The third type of the generating function. And the last one, so now P capital, P small, P capital and time. And f4, P small, P capital and time. Okay, so what else? Let me check what else I was planning to. Right. 4 possible forms of f. And of course, we can go reasonably easy. We will see. We can go, for example, from function f1, we can get function of 2, because what effectively the difference between this function and that function? Instead of Q capital, we have P capital, but you remember we have our Lagrange transformations, which allows us to make to remove any of the variables from the function and introduce a new variable, right? So transitions between these or those functions can be easily done using Lagrange transformations, but we will get everything naturally by deriving. But of course, I just wanted to emphasize that again, you can jump between any of these functions easily using Lagrange transformation, right? Although, except for example, if you want to move from function f1 to function f4, you will have to replace 2 coordinates, right? So of course, it will be more complicated than moving from here to there, right? All right. Okay, we still have 10 minutes, all right? And I feel like I want to mention something else. Right, anyway. All right, so this function f is going to give us transformation equation. So let's see how. Okay, So we need to go back to this again. I should have framed it because it's a very important point which we where we were, and then we digressed in order to discuss function of 1. So now we have to go back to this, right? And let's analyze function f1. Okay, I will probably move up here because it's difficult to write over there. Okay, we don't need all this. Okay, so let's look at function f1. f1, which is a function of q, q capital, and t. First generating function. Then next class on Tuesday, right, we will look at function f2. We're not going to play with function f3 and 4 because basically it's the same story, just more complicated, right? And I want to emphasize pretty much, yeah, as I said, these functions can give us a canonical transformation, will lead us to canonical transformation. And any of these functions you can use and you can get exactly the same transformation equations. Just sometimes this function can be easier to use, sometimes this function can be easier to use, so it depends on the situation, depends on the problem, right? But I'm telling you that any of these functions can be used, right, to get from this world to exactly this, to a different world. But again, as I said, any of these functions can provide exactly the same canonical transformation between these two worlds, right? Again, sometimes this is easier, sometimes that is easier. Right. Okay, so now we need to get actually final criteria, right? I raised this question, right? So, and we can get, of course, from here, right? So I will basically, let me label that this is 1. So go back to 1. Go back to 1. Right. And so now let me write that explicitly. No, I will first rewrite it and then I will start opening up the total time derivative. So pi qi dot minus h is a function of q small p small. qi bit then equals to, okay, first I will rewrite it completely. Right. Minus, now k, of course, k will be a function of what? Q's capital, p capital, and possible time dependence, our Hamiltonian in the new world, and plus df, and function f is the function of what? Q small, q capital, and t, and derivative with respect to time. Okay, you might have this question, at least when I was preparing this, many years ago. Of course, that question popped up in my mind. So how come we are in the Hamiltonian formalism, right? And in the Hamiltonian formalism, we treat what? Q's and P's, generalized coordinates and generalized momenta, as independent. How come that now over here we're using q small and q capital as independent variables? What's wrong? But the thing is, now we're solving a sub-problem inside of the Hamiltonian formalism. Right now it's not directly kind of connected to the Hamiltonian formalism, right? So we just want to develop a procedure to get canonical transformation. So we're just basically solving a sub-problem. And for that sub-problem, this function f is a function of q, small q capital. Once we solve this problem, once we get transformation equations which we need, of course, then we will go back to the Hamiltonian formalism, and of course, over there, q's and p's are linearly independent, right? So it's just small things which I wanted to mention, so that you wouldn't be confused. Okay, so now I want to just open it up explicitly, write this down explicitly. Okay, I will write here, okay, equal. So pi qi dot minus k, and that plus partial derivative of f with respect to time. I started with the last variable f, then plus partial derivative of f with respect to qi and qi dot. Again, tensor notation, summation is assumed, right? And then plus partial derivative of f with respect to q capital and q capital dot. Right. Okay, so now let's see, is what we have good enough for us? Of course, I can multiply, for example, everything by dt. And in that case, I will have here dq, here dq, here I'll have dt, here dt, dq, dq, right? And so now, since we treat q small, q capital, and t as linearly independent, you see all of these terms are good for us. We don't have to do anything. We don't have to do anything with them, right? Because what? Again, we will have dq and q, dq small, and of course q is a linearly independent, so it's good. This also q capital, it's our linearly independent. Here we'll have dt, dt, dq, dq. All the terms are good for us because all of these differentials of a linearly independent variables. So it means that this can be correct only when this equals to that, because q small is linearly independent, so it can be true only when this equals to that. Nothing else you can offer. If we had here, for example, let's say p small dot, that term would be bad for us. We would have to do something to get rid of that term, and we will do that with the function f2 next class. We will have to massage this. We will have to do some additional massaging of similar equation. But now it's perfect. Nothing else must be done. So then, of course, this must be equal to that, because again, q capital linearly independent, and of course the rest. This, let me use wavy lines, and this also must be equal, because yeah, you can multiply by dt the whole thing, and you'll have differentials of linearly independent variables. As a result, we're getting the equations which we needed, which will guarantee the transformation equation. So p small must be equal to a partial derivative of f with respect to q. As a result, equation number 1, right, pi equals to partial derivative of a generating function. Okay, now I should add subscript 1. Okay, sorry, I forgot. 1, 1, 1, and 1. Since, yeah, we decided to use function f1, but I forgot about the subscript, sorry. Right, so partial derivative of f with respect to qi. Then, second equation. The class is almost over, so I don't have to save space. So the second equation, this, you see these two terms on the same side of the equation, right? So this must be equal to that, but with minus. So it will be pi equals to minus, okay, let me shut down the phone. Let me write down the equations, and then we'll call it a day. Partial derivative of f1 with respect to qi. So the second equation. And the last equation is going to connect our Hamiltonians. Hamiltonian in the new world and Hamiltonian, okay, Hamiltonian in the new world and Hamiltonian in the old world. So k, all right, will be equal to h. Okay, k goes to this side, h to that side with plus. Okay, plus partial derivative of f1 with respect to t. So time. These are equations. So next class, basically, okay, maybe I will tell in words, and then next class I will write that down. I just wanted to write explicit dependencies, right? So I'm claiming that from here we can get transformation equations which will lead us to canonical transformations. How can we get transformation equations from here? Look, after differentiating, for example, this equation with respect to q, right? You have here q capital, q small, p small. So by inverting this equation, you can write q capital in terms of q small, p small. That's our first transformation equation. Then, once you know that, you can take that q capital, shoved it in the second equation, of course, after you differentiate the second equation. And as a result, you will have p capital will be in terms of this q capital will disappear. We will have again q small, p small. So as a result, we'll have p capital written in terms of q capital, q small, p small, right? Second transformation equation, right? And since we started from these equations, right, trying to satisfy those, right? So that must be equal to that. It means that these equations are going to guarantee that our transformation equations is the canonical. Our transformations is canonical. Transformations is canonical. And the last equation, it just connects Hamiltonian and Hamiltonian, right? Okay, then simple thing. It's reasonably easy to remember the structure of the equation. If you use function of 1, you see it depends on q small, q capital. You see in these equations, every time you differentiate that function with respect to those independent coordinates, with respect to q small, with respect to q capital. Over here, canonically conjugate quantities, right? If you here you have q small, here there must be p small, canonically conjugate. Here, if you have q capital, here there must be p capital, right? The only difference, the only place for troubles, these minuses. Sometimes pluses, sometimes minuses, right? And I saw several mnemonic rules in different books, but you know, those mnemonic rules, okay, idea of mnemonic rules, it's something simple which helps you to remember something. But those mnemonic rules, it's difficult to remember them. I don't see them as a simplification to remember these pluses and minuses. I would prefer just to memorize and where pluses and where minuses, then I have to remember those mnemonic rules, draw some diagrams complicated in order to get those simple pluses and minuses, right? I tried to use those rules for a couple of semesters and then I give up. No, me personally, I couldn't see any advantages of those rules. Or just open the book and see where we have pluses and where must be pluses and where must be minuses in these equations, right? Yeah, the structure of the equations I can easily restore, but pluses and minuses, if you don't use those equations for quite some time, of course you will forget, right? Okay, so yeah, enough of ending, right? So let's call it a day, right? So next class I will tell you about problems. Because it sounds like, yeah, great, you can move from the great world to the great world. Where are the troubles? There must be minuses. And the thing is, in order to get the canonical transformation equations, you need to know generating function. The question is, how can you get generating function? Go to the church, meditate, pray, right? I don't know, sleep on that, right? Hoping that light will descend into your head and you will see that generating function, right? Or of course you can reverse situation. You can say, if you have generating equations, right? Transformation equations, you can get generating function. But again, how can you get transformation equations? Basically, a vicious circle. And where you can break it, where you will be successful in to break the circle, there are no any rules. Right? Again, it's just basically, you will see next class or maybe in the class, we will try to solve a simple problem about harmonic oscillator, and you will see how many funky moves I will have to make in order to write down somehow this damn generating function. It will be hilarious how much of efforts I will have to make, finicky efforts, to write down that generating function. Effectively, it's great, elegant, beautiful, right? I cannot stop getting sort of mesmerized when I write all this down, but You got the point, right? Okay, guys, sorry for holding you, right? So we'll continue from this point next class, right? And I will tell you about my business ideas, right, and so on.